distribution and also the link to our data distribution system. Next slide, please. So as before starting, a small reminder of the upcoming GWTC3 webinars. We will have another webinar tomorrow about the population of merging compact binaries inferred with GWTC3, and another one in the new year, 20th of January 2022, about test of general relativity with GWTC3. Next slide, please. So let me go through the introductions. I'm Simone Mastro Giovanni, postdoctoral researcher at the observatory in Nice, and I will moderate the discussion for today. Let me just say that you might ask questions at any time using the Q&A chat box. We will reply there, and we will save some of your questions for the Q&A session that will be at the end of the talk. Then for our speakers will be Xingyu Chen from MIT, Subodip Mukherjee from Perimeter Institute, Maya Fishbeck, Northwestern University, Christos Karatanasis, IFE Barcelona, Martin Hendry from University of Glasgow. Next slide, please. But we also have a dedicated set of panelists that we will answer your questions in the Q&A chat box. We will have Constantin Lad from University of Paris, Surud More from UCA, Gergely Dalia, Ghent University, and Ashish Ghosh, Ghent University. So without further ado, I will leave the floor to Xingyu for the introduction. Thank you very much.
Thanks, Monet. So hi, everyone. So we know there are a lot of things we would like to answer. In particular, one of them is how fast does the universe expand? We want to know how fast the universe expanding now and how fast did it expand in the past. So to describe such expansion history, we can use a set of cosmological parameters, for example, including the Hubble constant H0, the omega matter, omega lambda, etc. So with features that allows us to relate for an astrophysical object at any given distance. That's what you see on the left-hand side of the first equations. How fast does this object away from us due to the universe expansion? That's captured by the redshift z on the right-hand side. In other words, if we can constrain such cosmological parameters, we are able to describe the expansion history of the universe. And among these parameters, the Hubble constant H, as you can see, set the fundamental scale of this expansion rate. Naturally, there are a lot of interest focused on measurement of the Hubble constant. Next slide, please. Okay, so there are a lot of cosmological experiments happen over the years, and the precision of such Hubble constant measurement has greatly improved over time. And as you can see in the figure I'm showing here, that is posterior of the Hubble constant measurement from various different experiments. However, these experiments, the result of these experiments are not consistent with each other. And this is where the gravitational wave measurement can start to play a role. Next slide, please. Yeah. So for gravitational wave, we are using this so-called standard siren method that's proposed by Bernie Hughes 30 years ago. The idea is the following. The gravitational wave sources measured by light, we are able to directly measure the distance to such gravitational wave source. And if somehow, for example, if we capture the electromagnetic counterpart of such gravitational wave source, we are also able to measure the redshift of this gravitational wave source by associating the electromagnetic counterpart to the host of the gravitational wave source. Then now we have both of the quantities we need, as we just showed in the equation in the previous slide. With these two measurements, we are able to constrain the set of cosmological parameters. And in particular, for LIGO, Virgo, Kagra sources, since they are relatively nearby, among the set of cosmological parameters, we are able to constrain the leading order term, the Hubble constant H0, the best. Next slide, please. Right, so this method has already applied. I see a breaking sound. There is a connection. So good. Okay, let me try to move a bit. Sorry for the.
Yeah, you're breaking a little bit, but I think it's going better now.
Okay, I just try to move and see if the connection is better here. And I guess I'll continue.
Yes, please.
Sorry for the connection. All right, so for the method I just described, this method has already been applied on the first binary neutron star merger detection, GW170817. What you see here is the Hubble constant measurement based on GW170817 and its electromagnetic counterpart. Next slide, please. Right. So what's great about gravitational measurements in cosmology is that, first of all, it is an independent measurement that is solely calibrated by general relativity. So as long as you believe general relativity, it should be automatically calibrated. And second, as I mentioned before, the most of the gravitational sources, they are relatively local, so they are very ideal for specifically the Hubble constant measurement. And finally, the precision of the Hubble constant measurement has been projected that in the next few years, we might be able to achieve a percent level precision. So that is a precision that's competitive with other cosmological parameters and possibly good enough for us to say something about the tension in Hubble constant we mentioned in previous slides. And next slide, please.
Thanks, Jinyu. So for the next bit, I'll be talking about our gravitational wave data, and specifically in this catalog, and then how we use these gravitational wave events to infer cosmological parameters, as Jinyu described. So from the gravitational wave signal, we have these gravitational wave events from compact binary mergers, and the signal looks something like the waveform you see there at the bottom. So there's this in spiral phase. The black holes or neutron stars get closer together, there's a merger, and then there's a ring down. And from the amplitude and the frequency evolution of the signal, we firstly learned the luminosity distance of the source that scales inversely with the amplitude of the signal. So that's, as Jinyu described, that's why these sources are termed standard sirens, because we can directly learn the luminosity distance to the source. We also, from the frequency evolution of the signal, learn about the masses of the source. But because frequencies are redshifted, the frequencies that we actually see in our detector tell us the redshifted masses. So it's related to the source frame mass by this factor of 1 plus z, where z is the redshift. Now we also, from having a detector of gravitational wave, from having this network of gravitational wave detectors, we learn about the sky position. So roughly where the sources occurred in the sky, and this will be important also for when we try to find counterparts or use a galaxy catalog. And then some other features we learn are the spins, the inclination and polarization of the source, which are less important for the analysis that we're talking about today. So next slide. So in this latest catalog that we just released, this third gravitational wave transient catalog, or GWTC3, so there was an overview webinar about that catalog earlier this week. And for the purpose of the analysis we're talking about today, this cosmology analysis, out of that catalog, we select the most confident events. So we're selecting events with a false alarm rate that's less than 1 in 4 years and signal to noise ratio that's bigger than 11. And this gives us 47 events from the first 3 observing runs of LIGO, Virgo, and Kagra. And 42 of them are binary black holes. So the vast majority of them, we would not expect there to be any electromagnetic counterparts. And in fact, in the 3rd observing run, we didn't see any confident electromagnetic counterparts to any of our events. So the one event that has a confident electromagnetic counterpart remains the binary neutron star event GW170817 that Chinyu described. So we don't have electromagnetic counterparts to give us redshift to our events. So we have to find redshift information in other ways. And the table that you see here is just a very small subset of this table that you'll find in the paper, which lists the events that we use and the properties that we use for them, like the signal to noise ratio, this inverse false alarm rate, the detector frame masses, and the luminosity distances. Next slide, please. Okay, so most of our events do not have any electromagnetic counterparts. So we need to find the redshifts in some other ways so we can get the redshift distance relation and infer the cosmological parameters. So the first method that we use is this source population method. So learning what the population properties of gravitational wave sources is very useful in its own, and there'll be another webinar entirely about that tomorrow. But for our purposes for inferring cosmology, what we use is the fact that our detectors are measuring this redshifted mass. So if we knew what the underlying source frame mass was, we could use this redshifted mass to learn the redshift. And we're also inferring luminosity distances. So then we can, from just gravitational wave signals alone, infer the redshift distance relation. But we don't know what the source frame masses of our events are. So we have to simultaneously infer that. And so the source frame mass distribution, for example, will look something like this left plot. So this shows as a function of black hole mass, what's the probability density of that black hole mass. So if the mass distribution looks something like this is telling us that in the universe, there are more black holes with relatively lower masses, and then maybe that distribution falls off as a power law. And we think that there is some feature, which is marked here by the vertical solid line, where the mass distribution maybe tapers off and then declines quite rapidly. And this feature, theoretically, we think that there could be a feature there due to pair instability supernovae. And what we assume for the purpose of this analysis is that this feature and the whole source frame mass distribution is the same at every redshift. So as we look back in time in the universe, the distribution of black hole masses is the same. But as you see in the middle panel, there's some distance redshift relation. So as we go out and see events at further distances, those events are also being redshifted more. And so what we actually see in our detectors is shown in the right panel there, which are redshifted detector frame masses as a function of luminosity distance. And so if I was plotting source frame mass on this plot, it would be this black line that you see would be a straight line. It's the same straight line that we saw in the left plot at around 40 solar masses. But because our masses are redshifted, you can see that feature in terms of detector frame masses gets larger and larger as we look back to further luminosity distances. And that this gives us a way to simultaneously infer the redshifts and the distances of our sources, as well as the underlying source frame mass distribution, which we don't know. So the only assumption we're making is that it doesn't evolve with redshift. But we also have to learn what the shape is on the left and the cosmology that dictates this distance redshift relation. So next slide, please. So for doing this analysis where we simultaneously infer the source frame mass distribution and the distance redshift relation, we have to use some model for modeling what the source frame mass distribution looks like. For this analysis, we use these same three models, which are familiar from our population analyses as well. So these are parametric phenomenological models. The simplest one is the one on the left, this truncated model, which is just a power law with sharp cutoffs. The middle one is this broken power law, which is just the power law, but now with a break in it. So there can be a different power law slope before the break and after the break. And the third one is this power law plus peak model, which is a power law with a Gaussian peak on top of it. And so all of these models, importantly, have some feature in terms of source frame mass. So either a sharp cutoff, a break, or a Gaussian peak. And these are these relatively sharp features that are giving us a scale so that we can infer from the detector frame redshifted masses, we have some scale that we can use to get a handle on what the redshifts are, as well as the luminosity distances. And so we assume that the locations of these features are in the source frame, do not evolve with redshift, and that allows us to do this analysis. Next slide, please. So the second method that we use to do cosmology with these events that don't have any counterparts is the galaxy catalog or the statistical standard siren method. So the idea here is that even though we don't have a counterpart to tell us what the host galaxy of our gravitational wave events are, we can just use every galaxy in the universe as a potential host of our gravitational wave event. And because we have some measurement of where these gravitational wave events happened in the sky, we don't have to use every galaxy in the whole universe. We just have to use every galaxy that falls within our estimate of the localization region of the gravitational wave events. And shown here are the sky maps of GW170817 and GW190814. These are exceptionally well localized sources. So you can see in terms of the right ascension and declination, the contours there are showing probability contours for where we think the gravitational wave event happened in the sky. Most of our sky maps are much, much bigger than this. So this is optimistic examples, but from here, we just take every galaxy, which is denoted here in the markers, and each of those galaxies has some redshift, which is shown in the color scales, and those contribute to a potential Hubble constant measurement, for example. We can use the gravitational wave distance and every redshift of every galaxy here to get some idea of what the Hubble constant is, and every galaxy now contributes. So we have to statistically marginalize over all of their contributions, perhaps weighting the galaxies. Maybe some galaxies are brighter than others, and so they host more stars, and so they're more likely to host gravitational wave events. And now I'll hand things over to Suvodeep to talk in more detail about the galaxy catalogs we use.
Thank you, Maya. So in the last slide from Maya, you have learned that one of the techniques to use gravitational sources to infer cosmological parameters is through using the galaxy catalog. So to get into the details and to understand what kind of galaxy catalog we need, so let's try to get a simple picture of how this method works. So here I'm showing you a simple cartoon diagram where a gravitational event with a sky localization error is shown by this gray patch. So what we are asking is that along that particular line of sight within the sky localization error, how many galaxies can be the potential host, which means we need to go deeper in the redshift, as well as we need to have a much higher completeness to make sure that a possible host of the gravitational wave source is present in our catalog. So with this, we can now list our requirements for constructing a galaxy catalog that we can use in our analysis. So next slide, please. So one of the primary things we need is the maximum sky coverage of the galaxy surface. Remember, the gravitational sources you can see throughout the sky in all the directions. So to enhance the possibility of measuring cosmological parameters from most of the sources, we need to make sure that we have an overlapping galaxy surface in full sky. We also need high completeness of the galaxy catalog. As I just now mentioned to you, it is essential that our host galaxy is also present in the catalog. So if the completeness is high, that catalog is more useful. From the previous slides of Sinu and Maya, you have learned that to infer cosmological parameters from gravitational wave sources, we need both luminosity distance and redshifts. As a result, the error bars on the redshifts from the galaxy surface needs to be pretty precise and accurate. And finally, we also need to make sure that we have done the systematic corrections because of peculiar velocity on the galaxy side to make sure that it is unbiased and also the errors are marginalized too. So taking into all this, if you go to the next slide, what we have constructed is a catalog called GLADE Plus, which we use in our analysis it combines about 6 different catalogs mentioned over here. It takes into account all the points that I have mentioned to you, and it's composed of almost 22 million galaxies. So we use this catalog for our analysis in GWTC3. So if you please go to the next slide. So here I'm showing you the sky map, which we obtain from these catalogs. So the sky, first of all, this particular catalog is full sky or nearly full sky. Here you are seeing a map of the catalog in color bar, where you can see a typical number density of objects around a few thousands. And in the Milky Way bar shown in green, shown in blue is slightly less depth. If you go to the next slide, and here you are seeing the overlap of a few of our gravitational wave sources on the galaxy catalog GLADE Plus. This particular catalog, you can see that for most of the sources, we have a sky localization error pretty bad. But as one of them, which is pretty good, which is also discussed by Maya, is GW190814, which is having almost like about 20 square degrees sky localization error. So we include all these events in our analysis and overlap that with the GLADE Plus catalog. If you go to the next slide, please. And what about the completeness? The completeness of the catalog, we also calculate for 2 different bands, the BJ band and the K band. In the left-hand side top panel, you are seeing the galaxy completeness catalog, which is defined as a fraction of galaxies with absolute magnitude brighter than a magnitude threshold, which is also mentioned in the legend of the plots. And you can see that we have typically about 40 to 50% sky coverage around a shift of 0.1 in the BJ band for magnitude threshold about less than 18.1. And in K band, if you see around redshift 0.1, we have about a 50% completeness. On the other side, in the gravitational wave sector, we have also measured luminosity distances to these sources. And here I'm showing you a plot on our distribution on the luminosity distance for these sources. And you can see that it's mainly at a lower distance. If you take a fiducial cosmological parameters from Planck 2018, you can see that most of the sources are in the low redshift around 0.1. So now what we will do is combine the galaxies from the GLADE Plus and the gravitational wave sources from GWTC3 to infer the cosmological parameters. Next slide, please.
Thanks, Shubhadeep. So I'm going to show you the results that we got out of this. As you have heard, we have two pipelines contributing to this analysis. The first pipeline is able to estimate at the same time cosmological parameters and population parameters, but cannot use any galaxy catalog. Whereas the second can use galaxy catalog, but requires the population parameters to be fixed. So what we did is run the first pipeline to find which of the mass models as the most preferred one, and then use that as input to the second pipeline to use galaxy catalog and improve our estimations. We find that the most preferred model is the Gaussian plus the parallel plus Gaussian peak, which the results you can see here. So here you can see posteriors that we got out of the first pipeline, and everything you see here is just using gravitational wave data. There's no galaxy catalog information at all here. And we plotted the parameters that we found that correlates the most with the Hubble constant. So starting from top to bottom, you can see the Hubble constant, then is the mu of the Gaussian peak, then is the maximum mass of the black holes, and finally is the merger rate evolution. And as you can see, we have an excess of black holes at around 35 solar masses, which gives scale for the redshift and provides constraint for the Hubble constant. So we do this for our three models, and we find the Hubble constant posterior. Next slide, please. We combine this posterior with the Hubble constant posterior from the O2, the BNS from O2 with the counterpart, and we got this plot for the CMAS models. So here you see four posteriors. The solid black line is the BNS with a counterpart from O2. Then we have the solid orange line, which is the parallel plus peak model, our most preferred model, followed by the dotted blue, which is the broken parallel. And finally, we have the dash green, which is the simple parallel model. Now, as you can see, our most preferred model gives the best constraint for Hubble constant, followed by the broken parallel, and the least favored model, which is the truncated parallel, a simple parallel model, actually gives a posterior that is less informative than the O2 BNS alone, which is an indication that this model is highly disfavored by the data and cannot fit the data very well. So we found that the most preferred model was the parallel plus peak, and we use that for our next pipeline. Next slide, please. Okay, so we use GLADE Plus catalog now with the next pipeline, and we select the K-band for the luminosities of galaxies. And we got this plot that you see here. So again, you see four posteriors here. The solid black is the BNS from O2 again. Then we have the dotted purple, which is the empty catalog curve that basically is running the pipeline with the catalog, but assuming that our galaxy catalog is completely empty, so it has no galaxies inside, and we get this posterior for the Hubble constant, which all the information that you see in this posterior comes solely from the population assumptions, no electromagnetic data here. Then we run with the GLADE Plus catalog, and we get the dust orange posterior. And the difference between the dust orange and the dotted purple is what the galaxy catalog brings exactly, all the information that the galaxy catalog brings to our estimation. And then finally, we combine the dust orange, which is our catalog posterior, with the solid black, which is the O2 event with the counterpart, to get the solid blue, which is the best estimation that we have so far, with a Hubble constant of 68 plus 8 minus 6. And then we ask the question, okay, what's the effect of our assumption on the posterior, so our population assumption and the galaxy catalog assumption? So to answer this question, we made the systematics plot. Next slide, please. This is the systematic plots that we made. So the top plot is varying the population parameters, whereas the bottom plot is varying the galaxy catalog parameters. So starting from the top one, we varied the population parameters that we found that correlates the most with the Hubble constant, those being the mu of the Gaussian peak, the maximum mass of the black holes, and the merger rate evolution. And as you can see, the posterior, when you change those, changes a lot. The peak moves around. So it's highly significant, the effect that those parameters have on the posterior. They're setting basically the position of the peak, as to say. Moving to the bottom plot, here we vary the galaxy catalog parameter that we use. We switch from K-band to BJ band in the galaxy catalog, and we also use K-band, but we didn't weight our galaxies based on their luminosities, just to find the schematics that we have from that. And as you can see, the posterior becomes less informative as we switch all of this, but the position of the posteriors remains the same. So it only marginally affects the Hubble constant estimation. That's another indication that population assumptions basically set the position of the peak. With that, I'm going to leave the floor to Martin for further discussion.
Thank you very much, Christos. So before we conclude, I'd like to briefly discuss a little more the robustness of our results and the validity of some of the assumptions that underpin our analysis methods. So our galaxy catalog method accounts for incompleteness in the GLADE Plus catalog, as we heard from Suvodeep, using calculations that assume a Schechter luminosity function, and also a sharp apparent magnitude limit, which we conservatively identify as the median magnitude in each pixel. So the upper plots on this slide compare the observed and predicted number counts of galaxies in GLADE Plus with the BJ band and the K band magnitudes shown on the left and right, respectively. So in each of those two panels, the purple dashed line shows the differential number count of galaxies as a function of absolute magnitude predicted for the Schechter function parameters that we assumed in our analysis. And the other colored curves then show the observed number counts in different redshift bins out to a redshift of 0.4. The colored vertical dashed lines, those show the absolute magnitude for each of those redshift bins corresponding to the apparent magnitude limit computed over the whole sky this time. So if our assumed luminosity function and magnitude selection function is a good model for GLADE Plus, then we would expect each colored curve to closely match the Schechter function prediction up to the corresponding dashed vertical line before dropping off at fainter magnitudes as the apparent magnitude limit kicks in. So we can see from these two upper panels that the observed curves do generally follow this behavior in both the BJ and the K band, although the agreement is slightly better for the K band. In the BJ band, there's an additional deficit of galaxies at low redshift. So it was that better agreement with our assumptions in the K band which motivates our choice of the K band to present our main results. Now, the lower panels on this slide show the results of a further study that we carried out for our source frame mass method. For each of the three mass models we considered, we repeated our joint inference of the population and the cosmological parameters, as we heard from Christos, but this time using an SNR threshold of either 10 or 12. And that yielded revised totals of 59 and 35 events, respectively. So we can see that for each of the three mass models, changing that SNR threshold does yield consistent posteriors on the Hubble constant. And we also find an excess of black holes around 35 solar masses in the power law plus peak model, irrespective of the SNR cut that we choose. So overall then, we believe that the assumptions underpinning our two methods are valid and our results are robust to the selection choices that we've made. Next slide, please. So to conclude, let me summarize our Hubble constant results. Shown here is part of table 4 from our paper, and it shows the key results from our source frame mass method, that's in the upper part of the table, and from the galaxy catalog method below. Now, the right and leftmost columns of numerical results, that's shown at the right-hand side of the table, those respectively include and exclude the bright siren constraints from GW170817. And all of the results shown there are for the highest density 68.3% credible interval derived from the H0 posterior. So we can see from the top part of the table that our source frame mass method results, as Christos highlighted, do depend strongly on our assumptions about the black hole source mass population, and in particular the mass scale at which the excess of black hole masses is centered. However, combining the black hole results with the information from 1708-17 does give similar H0 posteriors across the three population mass models. For the power law plus peak model, our result represents a 13% improvement over the corresponding GWTC1 estimate. That was the estimate obtained using data from the first and second observing runs, 01 and 02. For our galaxy catalogue method, our K-band and BJ-band analyses give even tighter constraints. And combining the K-band posterior with the information from 1708-17 gives our main result, which Christos highlighted a few moments ago, an H0 of 68 plus 8 minus 6. And that represents a 41% improvement over the GWTC1 measurement. Next slide, please. So we can see directly this improvement over GWTC1 by comparing the H0 posterior side by side as shown here. So the result for GWTC1 is shown in the left panel, and then our new result from this work is shown in the right panel. And this comparison underlines the key message from our results, that while 1708-17 is still strongly influencing our H0 posterior, we can clearly see that the addition of the GWTC3 dark sirens is making a difference and significantly sharpening that posterior. Now, the start of our fourth observing run, which is set for mid-December 2022, about 1 year from now, that will bring further upgrades to our detector sensitivity. And that should result in a further increase in our event rates and improved sky localizations, including, hopefully, some more bright sirens. So for 04, we also plan to make use of deeper galaxy surveys to provide better statistical redshift information for more distant dark sirens and to improve our pipelines by extending and combining them, and then simultaneously constraining both population and cosmological parameters. In short, therefore, we believe that gravitational wave cosmology has a very bright future. So I'd like to thank everyone for participating in this webinar. I'm now going to hand back to Simone, who's going to coordinate the answers to questions that people may have.
Thank you, Martin. So let me turn on my camera, and I hope that you all enjoyed this webinar. So we had a question in the chat box that we replied during the webinar, but there is still time for other questions. So please, if you would like to ask a questions, either write it in the chat box or raise your hand. I don't know if for technical reasons we can give the word. Okay, I see there is a question. Question on the source frame mass method. As your plot shows, the inferred H0 is degenerate with any evolution in the shape of the source frame mass distribution. So the uncertainty in that evolution gives us a gives a minimum systematic error on H0. So how will that evolution be constrained? Is there any way to measure the evolution other than measuring clustering redshift for gravitational wave events? I might pass this to Maya.
Yeah, thanks. Thanks for the question. That really is the key question, and I think this is very much still under development. I think there are several avenues to kind of explore once we get the statistical uncertainties low enough that we would be worrying about this systematic. And I think the first one is just theoretical calibration, which is tricky because I think our current inference on the mass distribution is quite different from what we expected from theory, and like the location and also kind of the shape of what is happening with pair instability, and that pair instability feature is puzzling. So that's definitely a big challenge, but I think we are definitely motivated by theory that tells us that that feature is relatively independent of things like metallicity, and using that as a scale that is redshift invariant. But I think, yeah, there are definitely other ways to try to do this. Essentially, the redshift evolution, or the evolution of the source frame distribution with cosmic time, that's going to be very weird if that exactly mimics the cosmic expansion, because even if the location of different features move, the shape of those features, we probably expect those to be the same. So there are definitely more things we can do along that lines. So I guess short answer is that we will need some calibration, which is kind of normal in doing these cosmological analyses, but it's definitely not as clean as getting an electromagnetic counterpart, or, as you say, doing this clustering with a galaxy catalog. So I think definitely all these things will work together, and this is just the beginning.
Thank you very much, Maya, for the reply. And we do have other questions that are going to be replied either by chat or by us. So the next question is from Huri. Can the measurement of gravitational wave in different bands be used for estimation of primary and secondary mass and redshift, or at least for improving the results of the statistical method you are currently using? And I would like to ask Gergely if he can answer this question, please.
Yeah, thank you, Simone. So yes, if we can have an electromagnetic follow-up and we observe the source with different telescopes, so in the radio band and in other bands as well, then we can infer some parameters of the host using these measurements. So if we can perform an electromagnetic follow-up, then these could be very useful pieces of information.
So I see there is a little follow-up by Huri that says not EM, just gravitational waves. And yeah, so I think there is another question that appeared in the chat to everybody by Mark. I'm going to read it. Distance from the Hubble constant from this analysis compared to gravitational wave methods, how are they significantly different? So maybe I can ask Konstantin to answer this question.
I'm not sure I understand the question entirely. Are you asking whether the cosmological values are compatible from EM and only gravitational wave data analysis?
I think the question here is, yeah, more related to, yeah, the scale. So please go ahead.
Sorry, I'm not sure I understand the question. Maybe you can take it.
Okay, so I think I can, yeah, I can pass it then to Sudip, please.
Hey, thanks for the question. So if you understand it correctly, So we want to emphasize that Sinu was mentioning in the very beginning that for the gravitational wave sources, the distances are pretty much accurately measured without any further calibration if the general theory of relativity is correct. So when we compare that with our measurement of the Hubble constant, which we get, we do not see any significant departure from any other non-GW sectors, such as supernova type 1a, barrier BAO, or strong lensing, and of course, semi measurements. So right now, we do not see any significant departures in the distance measurements we have inferred in comparison to any EM sector. I hope that answers your question. So I see a question once more at supernova standard candles versus GW measurements if the Hubble constant. I am not very sure what you exactly mean, but if you can clarify, we can get back to your answer again. Thank you.
Okay, so let me ask if there are any other questions, since we would have some other time to reply. Otherwise, we can go ahead and close the session. I see there is actually another one from Gregoire. I have another question. Is H not posterior using a galaxy catalog only mainly driven by GW190814? Archisman, would you like to take this question?
Yeah, sure. It is in fact not true that the H0 it is in fact not true that the H0 galaxy catalog posterior is driven mainly by 190814, but 190814 plays an important role there.
Thank you very much, Archisman. So I think we can I ask Martin to answer the question to reiterate the question by Yuri. Maybe Martin, you can speak up, please.
Yeah, sure. Thanks, Simone. Thanks, Yuri. Perhaps we slightly misunderstood your original question. I think the answer we gave was still an important one from Gergi about the importance of multiband EM observations. But I understand you were really asking about multiband gravitational wave observations. And of course, there is a lot of interest in estimating the Hubble constant and other cosmological parameters from other bands in the gravitational wave spectrum. So specifically, if you're talking about a particular event that would be seen first in the early in-spiral stage from, for example, a space-based detector like LISA, and then seen later, possibly some years later, in ground-based detectors, then yes, potentially this could help to verify, at least provide a important sanity check on the estimation of the masses. More generally, however, the opportunities to determine the Hubble constant from spaceborne detectors will be really quite extensive. There will be opportunities to use different sorts of events like extreme mass ratio in spirals. There's been some excellent literature on that in recent years. So, fundamentally, the issue is still not having a guaranteed electromagnetic counterpart, possibly no electromagnetic counterpart from binary black hole mergers. But at the same time, the ability to more precisely predict both the time and the sky location of future ground-based mergers by first seeing them in the in-spiral phase with a spaceborne detector could be an important future development for gravitational wave cosmology as well.
Okay, so there is another questions in the chat box, and this is, am I right if I say that your result for H0 is more in agreement with Planck data inferred from plots on slide 23? So let me first ask Konstantin if we can move to slide 23, just to see the plots. And I would ask Singyu to answer the question if possible.
Right. Thank you for the questions. I guess with our current uncertainty, we are not able to make any statement about whether it is with more agreement with Planck or Hughes value. It's just too early for us to say. There is some good reason for us why it seems that we have better constraint at lower H0 value, and that has to do with the completeness of the galaxy catalog, while we don't have that good constraint for the higher value of H0. But still, with current uncertainty, we are not able to say which of the two is preferred.
Thank you very much, Singyu. So let me ask if there are any other questions that you would like to ask. I'm just giving you a few seconds if you are finishing typing. So while this time passes, let me say that these slides will be updated on the public DCC link that Surud sent to the chat. So you can dig back into the chat and find the public DCC link of the cosmology paper, from which you will find also a link to these slides. Moreover, you will find the slides on and the registrations on YouTube that will stay there. And yes, I think that is everything. So I would like to thank very much everybody for attending this webinar today. A particular thanks goes to our speakers and our panelists. And I would like to say goodbye, and I hope to see you for the next webinar tomorrow at the same time about populations results for the compact binary coalescences that we observe. Thank you very much to everybody, and have a good day.